A sensible approach to studying the theory of electromagnetism is to accept the mathematical validity of the Maxwell equations, and then look at individual aspects of these equations, define the parameters, and decide how they depend on each other. A good place to start is the concepts of charge distributions and charge density. Charge density is represented in the Maxwell equations by the parameter ρ, which is a function of position and generally also a function of time. It appears in the first Maxwell equation on the right-hand side. The divergence of D, the electric flux density, is always equal to the charge density, which is a function of position and time. Charge density is typically represented by the Greek letter ρ. The cartoon at the bottom illustrates the concept of charge density. Here, some 7 positive discrete charges are distributed inside a box. This is a charge distribution. If the total charge in the box, which is 7 positive charges, is divided by the volume of the box, delta V, we have the volume charge density. Whereas in some microscopic situations, a few elementary charges may be tracked and distinguished, as just illustrated, the typically 10 to the power of 23 elementary charges present in most macroscopic problems cannot be distinguished and tracked. It is thus convenient to neglect their discreteness and treat these charges as a charge continuum. Within this continuum of charges, the charges are distributed as charge distributions, and at each point of this continuum, a charge density may be defined. As with mass densities, charge densities ρ can be defined for volumina, for surfaces, or on lines. Charge densities are a function of position, and in time-dependent electromagnetics, they are also a function of time. The formal definition of charge density at a point xyz involves a limit, which is not convenient in problem solving. Charge density is a scalar, and in the SI system, the unit of volume charge density is coulombs per cubic meter. The cartoon at the bottom of the slide illustrates a typical macroscopic situation with 2 charged clouds, one being negatively charged and one being positively charged. Defining a Cartesian coordinate system with an origin and an x, y, and z axis, for each point in space, a charge density ρ can be defined as a function of the position vector r, indicated here as a vector with an underscore tilde. In contrast to mass density, electric charge density can be positive or negative. The charge distribution in the cartoon is very positive for large Z and tends to be negative for low z and large x and y. The definition of charge density as the infinitesimal ratio of charge per volume means that integration over the charge density gives the total charge Q in a volume. Generally, 4 situations can be distinguished. A point charge Q, where the total charge of that point is given by little q in Coulomb. A line charge density, where charges are distributed along a line, typically a straight line. A surface charge density, where charges are distributed over a surface. And finally, a volume charge density, where charges, which can be positive or negative or both, are distributed inside a volume. The respective charge integrals are detailed on the right, for volume, surface, and line charge density. Depending on the number of dimensions, these integrations are either 3-dimensional, 2-dimensional, or in the case of line charge density, 1-dimensional integrations. This sketch shows a very important macroscopic charge distribution, namely that of a rainstorm cloud. Such storm cells typically extend over several kilometers in height and feature a large temperature gradient, with minus 35 degrees Celsius at the top. Although not every detail is known, it is understood that upwinds separate charges with positively charged ice particles at the top of the cloud and negatively charged rain droplets at the bottom. This means there is a large potential difference between the bottom of the cloud and the ground. This causes the lightning discharge. Performing a volume integration of the charge density distribution at the bottom of the cloud gives therefore a total negative charge Q, whereas a similar integration at the top of the cloud will give a Q that is positive. While it has been shown that the bottom of the cloud also contains some positive charges, the bottom of the cloud is predominantly negatively charged. In order for a lightning strike to occur, a leader has to develop that eventually extends to the ground, creating a conductive path for the lightning strike. The so-called leader is a good example of a line charge density. Integrating this line charge density gives a total charge Q that is negative. The question arises what causes electric charge and the distribution of electric charge. Electric charge is carried by microscopic particles, and the most important microscopic charge carrier is the electron. Often we denote the electron as a little circle with a minus sign in it, or just a minus sign, or the letter E with a superscript minus. We should, however, not forget that the electron is a true point particle and that quantum mechanically its location is not always well defined. Each electron carries an exact discrete charge, which is approximately 1.6 times 10 to the minus 19 Coulomb in the SI system of measurements. The mass of the electron is approximately 0.511 mega electron volts per c squared. This unit of mass measurement is particularly convenient when discussing electrons in a microscopic sense, since it does not involve any power of 10. The calculation on the right shows the unit conversion to kilogram, which is the SI unit, using the equivalence of energy and mass. E equals mc squared. In SI units, the mass of the electron is 9.11 times 10 to the minus 31 kilograms. An important feature of nature is electric charge duality. The electron thus has an equivalent positively charged particle, the positron. We might indicate a positron as a circle with a plus sign inside, or simply as E superscript plus. The positron has exactly the same mass as the electron and the same magnitude of charge of 1.6 times 10 to the minus 19 Coulomb, however positive. Interestingly, the positron does not have the same sort of importance that the electron has. This is because it is also an antiparticle. In our world, antiparticles immediately annihilate once they meet particles. Since there are many electrons in our world, a positron will immediately combine with an electron, and the combined mass will be emitted as two gamma-ray photons, each having an energy of 511 keV. If the positron is not the important positive charge carrier in our world, which particle takes that place? The most important positive charge in our world is the proton. We denote it also with a circle and a positive sign inside, or simply with the letter P. In contrast to the electron, the proton is not a point particle. It has a finite radius. The radius is approximately 1 Fermi, 1 times 10 to the minus 15 meters, which also equals 1 femtometer. The mass of the proton is much larger than the mass of the electron. It is 938.3 mega electron volts per c squared. The student might want to convert this to kilograms using the procedure described on the previous slide. Protons exist in the most abundant element of our world, hydrogen, right at its center, as the positive core of the atom. Since the electric charge of the proton is Qp equal plus 1.6 times 10 to the minus 19 Coulomb, the positive charge of the proton at the center of the hydrogen atom thus neutralizes the negative charge of the electron at its periphery, so that the atom as a whole is charge neutral. This illustrates that positive and negative charges balance each other. Importantly, when two charges are separated, they experience a force, according to Coulomb's law. More formally, one may phrase, two charges experience equal forces along the line that connects them. The directions of these forces depend on the respective signs of the charges. The two charges attract each other when they have opposite signs, and they repel each other when they have equal signs, if they are both positive or both negatively charged. The magnitude of the forces acting on the two charges is given by Coulomb's law as F equals 1 over 4 pi epsilon naught times Q1 Q2 divided by r squared times a unit vector that points in the direction of the force. In this equation, the factor 1 over 4 pi epsilon naught, where epsilon naught is the dielectric constant of vacuum, this factor is characteristic of the SI system and the consequence of it. Q1, Q2 represent the magnitudes of the two charges interacting with each other, and the r in r squared is the distance of separation between the two charges. Coulomb's law strictly only applies to point charges Q1 and Q2. However, often charge distributions, when they are positive or negative, are sufficiently separated that they can be represented by point charges. Interestingly, the concept of charge density and charge distribution can also be applied in the microscopic world, where there are only discrete charges present. This is because of the quantum mechanic nature of the electron, which doesn't always have a defined position. The uncertainty of position associated with electrons is often described using charge clouds. Such charge clouds occur, for example, in covalent bonds that exist, for example, in silicon crystals, where they fix the silicon atoms in place. The macroscopic concept of a continuum of charge density is thus also very applicable in microscopic situations such as this, illustrated here through a simulation of the electron density in a silicon crystal. Looking through the crystal, the black dots identify the silicon atomic cores. The cores are connected by covalent bonds, each made up of 2 electrons. The red color indicates that the electron density is particularly large in the covalent bond between atomic cores. A typical problem of classical electromagnetism is the calculation of a total charge from a given charge density. Such a problem is illustrated here. A cube is given which is filled with charges, according to rho v equals x times x squared times e to the power of minus 2z in units of millicoulomb per cubic meter. So this is a volume charge density. The sides of the cube are 2 meters in length. The problem is solved by carrying out a volume integration over the given charge density. This integration gives a total charge of 2.62 millicoulomb.